So in this video, our learning target is I can translate between multiple representations of exponential functions. So we'll be looking at exponential functions and translating them between equations, tables, points, graphs, and situations. So that's what we will be working through on this. Remember, exponential functions are one of our three functions we've talked about all year. This is where the x is in the exponent. That's what the exponential function is, where x is in the exponent. So let's look at these. On example A right here, we are given let me change colors. And let me put it on a pen. There we go. We are given an equation, y equals 5 to the x, and they are evaluating it for where x is 2, where x is 3, and where x is 4. So where x is 2 right here, the 2 goes in the exponent, 5 squared is 25, so that's our y. Where we're looking at 3, 3 is in the exponent, 5 raised to the third means 5 times 5 times 5, and that's 125. Here, where x is 4, it's 5 to the fourth, 5 times 5 times 5 times 5, which is 625, so that's how they came up with all of these. Here on part B, they're doing something pretty similar. Instead of y equals, it's t of n equals 4 times 3 to the n. So you take the 4 and multiply it by whatever 3 raised to the n power is. The domain we're using is negative 3 and 6. So for negative 3, you have 4 times 3 raised to the negative 3. Here they're showing you that that 3 to the negative 3 is 1/27. We'll talk about that in the next unit. And 4 times 1/27 is 4/27. Same thing here. You have 4 times whatever 3 to the 6th is. 3 to the 6th is 729. So 4 times 729 is 2916, and there is that. So the multiple representations we have translated between here are from an equation to a table. Here it says evaluate each exponential function for the domain -2, 0, and 3. And we're going to use our calculator for that. For A, y equals 4 raised to the x, we are going to type in to our calculator 4, and then we hit the raised button right here to the x. So we have 4 raised to the x instead of y equals. Of course, in our calculator, we have f of x equals. We hit enter, and we can see the graph for this looks just like that. We want to look at specific points, so we're going to hit Control T to get our table. Those points were -2, 0, and 3. So for -2, we're going to have to move up a couple. -2 is 0.0625, and there's that, and 0 is 1, 3 is 64. So those are the points, and all that means is 4 raised to the 3, 4 times 4 times 4 is 64. 4 raised to the 0 is 1, and then the 4 raised to the -2 is the 0.0625. And that's all you have to do to be able to evaluate the exponential function for that domain. Let's look at one of the ones that's a little different. Let's look at C, where we have g of x equals -2 times 3 to the x. So -2 times 3 to the x. We can clear this, add a new graph. So we have -2 times 3, again we use that raised to the x. And so we have our -2 times 3 to the x. We hit enter. A little bit different here. This one is decreasing as you go along. Let's hit Control T and look at our table. And again for -2, we have -0.2 repeating. For 0, it's -2. And for 3, it is -54. So it decreases very quickly. That's true of exponential functions. They move pretty quickly once they start going. Okay. So let's look at our next little bit. We have gone from an equation to a table. Now we're going to use a situation. This problem says, suppose 20 rabbits are taken to an island. The rabbit population then triples every half year. The function f of x equals 20 times 3 raised to the x, where x is the number of half-year periods, models this situation. How many rabbits would there be after 2 years? Well, the first thing you have to think about is the fact that 2 years is actually 4 half-year periods. So we're going to plug in 4 for our x right there. 3 raised to the 4 is 3 times 3 times 3 times 3, which is 81. So 20 times 81, and we get 1620 for our number of rabbits. On this example number 2 here, suppose 10 animals are taken to an island, and then population of these animals quadruples, which is times 4, every year. Function f of x equals 10 times 4 to the x. How many animals would there be after 6 years? Well, we can just do, plug this 6 in for our x, because here x is number of years. Let's make this a little simpler for ourselves. Let's go to our calculator. It was, if I remember right, 10 times 4 to the x. So we can do 10 times 4 raised, except not the x, we know we're looking just for the 6th. And so we can get 40,960. We could also do this on our calculator. There we go, on the graph, excuse me. So we could do 10 times 4 raised to the x here, and we can look at our table, and when x is 6, there it is, 40,960. So 2 different ways we can work through that problem. So there we have translated between a situation and a point. We found a specific point. Okay, next we're going to be looking just at the graphs. If you want to graph an exponential function by hand, all you have to do is the same thing we did at the beginning. We take an x value, and here we're going to use -2. We plug it in for our x right there. We get 3/4, so we have the point -2, 3/4, which is this one here. Same kind of thing, we plug in -1 for the x, and we get 1.5. So we have that point, and we keep on going. With 0 is 3, and then we have 6, and then we have 12 way up here, and that's our exponential function. To graph these on your calculator is nothing different than we've done any of the rest of the year. Here we have 0.5 times 2 to the x. Let's look at that. Let's close this out and this out. So we have 0.5 times 2 raised to the x. 0.5 times 2 to the x. And there's our graph for it. We can see that it crosses the y-axis right here at 0.5, and then it just goes on up from there. The other one that the example was asking for was -0.5 times 2 to the x. Let's see what that change does. So we'll hit tab to reopen. Here I'll move up a line and change this to a negative. Same kind of thing, except it's heading downward. Our y-intercept here is -0.5. So it seems as if this number in front is the y-intercept in this case. Okay, back here, let's look at our next piece. Scroll down a little bit. Okay. On this last section, we're just going to be doing some matching. So we have 2 raised to the x for number 15. For 16, we have -2 raised to the x, so the opposite of that. For 17, we have 1/2 raised to the x. And for 18, we have a negative half to the x. So we need to figure out what the difference is between all of these. So let's see what's going on. On graph A, we're starting low and then closing in towards the x-axis. On C, we're starting high and then closing in towards the x-axis. On B, we're starting on the x-axis and then increasing greatly. And on D, we're starting on the x-axis and decreasing greatly. So let's graph one of these, and I bet we can use just that one graph to figure out the rest. So we are going to add a graph, and we're going to do 2 raised to the x. And so 2 raised to the x starts at the x-axis and then increases greatly, which means that looks like B. So 15 is B. The opposite of 2 to the x, starting at the x-axis but not increasing but decreasing, would be D. And then we have to figure out which of these, 17 and 18, is A and C. Let's graph 17 in our calculator, and then we can see where it goes from there. So we have 1/2 raised to the x. Let's do 1/2, and then we raise to the x. And so it starts high and then comes in down towards the x-axis, which is C, which implies that this then would be A. So it looks like fractions start high and end low. Fractions between 0 and 1, I guess. And integers start on the x-axis and then get very high or very low. So that's kind of something we can generalize to help us with problems after this. And so we have translated between multiple representations of inverse variation functions. We've moved between graphs and equations and points and tables and situations.